So the best way to understand a container is just to think of it as a process, just like any application that could run on your machine. A container is simply a process that's typically isolated, much more so than a traditional process. And so to understand a container, then it's helpful to understand processes. And to understand processes, it helps to revisit the basics of forking a process using the fork system call. All right, so I've got a little console application. It doesn't do much other than print out the PID of the current process. So if I run this again, I'll get a new PID. And this is a little C++ console application. If I hop over to the code here, it's in a fork.cpp, and I'll have the repo with this inside of it linked into the video description. So the bulk of this right now is just getting the PID of the current process and dumping that out to the screen. And then I add some new lines before and after. So now if I modify this, I can make a call to fork. And instead of PID, I want this to be called fork PID. And then before this, I'll dump out before fork. And then after, I'll dump out an after fork message. What do you think this is going to produce for output? All right, so I'll come over to the command line. Got a little Linux environment inside of here. There's a make file, so I can just run make here to update my little program. Got a warning about the PID. I can ignore that for right now. So if I run my program again here. So we get the PID just like before. But in the case of our messages, we see before fork, and we see after fork, and we see that twice. It's really interesting. Well, that's a function of the fact that when we call fork, we're creating a child process by duplicating the current process. And then the current process is referred to as the parent process. So we have the child and the parent process that both resume running at the point of the fork. And thus we get our message twice here. And the reason we see before twice is because this is actually stored in a little buffer because there's no new line to print this out. If I had had a new line on the end here, that would not have been duplicated. But because it wasn't, then it was stored in a buffer. After fork comes along, and then we print out two new lines here. That triggers the dump in both the parent and the child process. And thus, we get a duplicated message here, before fork and after fork. So if I put in a new line here, I can stop that. Can even put it here just to be safe. Build it again, run it again, and there you go. Now I just have before fork, one of those. And then after fork, we have a message twice. And if we hop over, we can actually determine whether or not we are the child process or the parent process when the code is running here, because remember, both of them will fork and run from the same point. If we take a look at that fork PID, so if fork PID, if that's equal to 0, that is the new child process. And then we could just do an else, but I'll do an else if here. Fork underscore PID is greater than 0, and that means this is the parent process. Okay, so what we could do is we could print out child here, and then let's do this. Let's get the PID in the line there, and then do the same for the parent. All right. I'll build again, run again, and there you go. You can see here is the parent's PID, and that makes sense. That's 257, which matches the original PID that we printed out before the fork. And then in the case of the child, the PID is 258. Now don't confuse that with the fork PID, which is separate. If you want to see what the fork PID is, I could add some additional output here. Fork underscore PID equals, and we'll dump out the fork PID as well. And I'll do the same thing for the parent. Save that. Come back over, build, run, and there you go. So now the actual PID is here. It's the first number. The second number is the return result of the fork function, which I call the fork PID. So in the case of the parent, which is 272, just like up above, in that case, the parent gets a fork PID of 273, and that's because that is the PID of the child. So the parent then gets to know what the child's PID is. However, in the case of the child, it doesn't get anything but 0 back, which tells it that it was the child that was forked from that point. That way you can have different logic for the parent and the child. All right, so now that we understand that, we're going to make a slight change here. Right before the call to fork here, we use another method. This one's called unshare. And to this, I'm going to pass clone underscore and new PID. Basically, I'm requesting to unshare the PID namespace at this point in time. And that's going to have an impact on the PIDs that we see in the output. In fact, let's do this. Let's duplicate showing the PID right after, see if that has any impact. And then we'll go about running the program just like before. All right, so go ahead and build, run our program again. All right, so let's step through this here. 288 initially for the PID. And then after calling unshare, we still have 288, so it didn't affect the parent process ID. And if we keep going here, before the fork, after the fork, all right, and the parent still has 288, just like before, and it gets a fork PID of 289 for the child. All right, that's all the same as we had before in terms of behavior. But then when we get down to the child side of things after the fork, the child, it sees its PID as PID 1. It doesn't see 289. And that's because when we call unshare and we ask for a new PID namespace, that will affect any children that we create. And thus our child here has its own PID namespace where it sees itself as the init process. So that's a first step in understanding what exactly a container is by taking a new child process and walling it off into its own PID namespace so that it thinks that it is the first and only process on the machine.